Hi friends, welcome back to the next installment in our series, the Ray Tracer Challenge by James Buck, where I implement a ray tracer in Rust, a language I've never used before. We are going along this one and learning Rust from scratch while implementing something graphically wondrous, a ray tracer. So in the last chapter, we were able to render a sphere. Let's just take a look at this one. We rendered this sphere here, which is actually a three-dimensional sphere, but as you can see, you cannot see the three-dimensional aspect of it yet because it is not shaded in any way. It is essentially rendered in three-dimensional space, but we don't have lighting yet, so you don't see it being pronounced in the three-dimensional sense we would assume here. So even though we have this silhouette, we now want, in chapter 6 of the book, to implement lighting for this sphere. So in order to do that, we have to actually take a look at certain mathematical aspects of rays and how they can be reflected, and we need to implement some stuff based on this. So a first thing that we need to do for this is implement so-called normals. And what is a normal actually? Let me get my tablet here so I can explain this one to you. If we have some sort of surface, let's say we have this surface here. A normal would always be the vector which is perpendicular to this surface. So we could actually calculate the normal at any given point of this surface, like this one, for example, or this one, or this one, or this one. And always the normal would be perpendicular to the surface. So those would be the normal vectors for this surface at the given point. And essentially this is what we will be now calculating first, because the normal is actually very useful in all kinds of further calculations, because knowing the perpendicular vector, actually in the perpendicular in 3D space, even though I've only shown it here now in 2D space. So maybe I can try and draw this. Let's say we have something like maybe this here in three-dimensional space, and we have now our point like here. The normal would be somewhat like this. So it would then be here and here, I guess. Those two would be essentially then be perpendicular. So it is the vector which is perpendicular to our face where we are looking at based on a given point of this face. So this is really useful for us in all sorts of different 3D calculations, because knowing this vector we can do a lot of different other calculations and stuff, like, for example, easily calculate reflections and things like that we need in order to determine how this specific point on the surface should be shaded. So let's get going and implement this behavior, or better said, this functionality, I would say. So first thing we actually need to do is we need to extend our sphere a little and allow our sphere, or better said our intersectable, because we want this essentially for any of our body objects later on, to provide us with a new method. But first things first, let's get the tests here that we need. Let me just copy them over. So we have a new test here. Let's get the first one from my preparation over here. There we go. And let's make this one run. Essentially, this test does nothing more than creating a new sphere, calling a new function on this sphere, which is called normal at. Then it is given a point on the surface of the sphere. In this case, we have this unit sphere, you might remember, which is has a radius of 1 in all directions, x, y, and z. And so the point on the x direction 1 and 0, 0 on the other ones is exactly the point lying on the outer radius of this sphere. Let me show you quickly. If we have this sphere and a coordinate system like this, which goes through the sphere, then this is our 0, 0, 0 point here. And the point we are actually taking a look at is this one here. It is the point on the x-axis, just on the outer shell of the sphere. So let's calculate the normal at this point, and then we assume that the normal of this point is actually the vector just pointing into that direction. And you can easily imagine that by yourself if you think about this point. Let me make it a little bit bigger here. This point on this axis here, if this would be a sphere, the vector actually the perpendicular vector to this sphere at this point would go something like this. And essentially it's only this vector we are calculating here. This is the normal then. So yeah, let's calculate this, I guess I would say. So let's first of all add this normal add functionality here we need. But as I've said, I would like to add it to our intersectable trait, because we will need it on every of our body objects later on, which all will be implementing this intersectable trait. So let's implement this one here, and of course it gets a self and it gets a point, which then is a tuple, which is a tuple. So, and it returns essentially a vector, which is a tuple as well. So let's define this. Let's import the missing tuple here so that the compiler knows what we are talking about. And now, of course, it is telling us that this body intersectable here does not implement this readily. So let's add this one. Let's create a normal add here, which is a self, gets a self, and a point, which is a tuple, and the tuple is returned. We are matching this, and once we are knowing that it is a sphere, we are simply dispatching this to the sphere and giving it the known point here. So that should be all we need to do for this intersectable, and now things should actually work with our body. Another thing we now need to implement here is we need to implement it on our sphere, as the compiler is already complaining that we now haven't implemented fully the intersectable trait here, and it is obviously right about this. So let's implement this. Fn normal at we need the self because we need information about our sphere, and yeah, let's implement this one given the point here, which is a tuple, and a tuple is returned. So how would we actually implement this normal on a sphere? And let's get back to our drawing board here. It is essentially quite easy if we kind of think about our sphere as a two-dimensional object. Let's just take a look at the two-dimensional space here. Let me get this color here and maybe go a little bit over here. So we now have, we now have our sphere here and our coordinate system, which is centered in this sphere. So now to calculate the normal on any of the points around this sphere, any of the points around here, we essentially only need to calculate, if you think about it, the vector which goes from our origin point in the middle of this one to an arbitrary point on our sphere's hull in 3 dimensions or 2 dimensions. We don't care about that here because it is essentially the same. And this one, for example, we want to calculate it for this point. We calculate this vector here, and this vector is exactly pointing out perpendicular to the sphere's hull then. You can easily think about this, because where would be all the perpendicular vectors, for example, this point and this point and this point? They would of course be something like this, something like this, and something like this. And if I now make them a little bit longer in the direction to the center of this one, you can see that they are all joining there. So essentially our normal vectors of this sphere, of this unit sphere, which is in the center of our universe at the 0, 0, 0 position, is the vector which is going from the origin point out to the given point. And we can easily calculate this vector, of course, because this is nothing else than our given point minus the 0, 0, 0 point. And yeah, then we normalize this just to make sure that we have a unit vector there, because a normal should always be a unit vector, because it eases all of the different calculations later on. So let's simply normalize this one. We implemented this on vectors. I hope we did. Yeah, we did. So essentially now this is our normal, which goes from the 0, 0, 0 position to our given point on the sphere, and it is normalized, and we have our normal implementation. So let's check if the tests are running. Cargo test. They are compiling and they are running. So our test below here, which is calculating the normal on the x-axis, is running out well. So yeah, I guess we are bringing in some more tests then. So let me copy in here the tests for the y and z-axis as well, just to make things complete and to check that it is working for all the different axis points as well. So now we have on the x-axis here 0.100, we have the y-axis with 0.010, and we have the z-axis with 0.001. So let's check if this is running, and it is working out. Yeah, so now we have those x and y and z axis checks, but what is with a point not on one of those axes, but somewhere on the hull of this sphere? So let's add a test for this as well, which would be a little bit more complicated, as the values, of course, would be a little bit more complicated. We might need to import this floating point value here. Let's get this one, our floating point type, better said. And essentially now as a point we are using the point which is the square root of 3 over 3 3 times, which lies somewhere on the hull on the side, just inside the sphere, just on the outside of the sphere as well. And there we are expecting the same outgoing normal that we are expecting with all the other tests. So let's run the tests. Yeah, so we implemented a normal calculation for our sphere. Where is our calculation? There it is. So now we can actually calculate normals. So let's see. We can calculate normals here by using this technique, going from the center here, the origin, and then to the point we want to calculate it and extending it out. This is our normal vector then, which points into the right direction. So the next thing actually is we need to take a look at transformed spheres, because we cannot only have a sphere, which is at a unit sphere at the center of the coordinate system, you might remember for this intersection we assume that it always is this way, and we are simply transforming the ray then in order to calculate our intersection point then, and it works out fine. And you could think of, okay, we might be able to do the same thing with the normal then during the calculation. We could just transform this point on the sphere by the reverse of our transform, so we would have the same point. But the problem with this is something like, let's check this out graphically, because I guess it's easier to be explained then. So let me make a new page here, and let's assume we have our usual sphere here. Okay, so this works out quite okay. So we could have a normal here, and we could have a normal here, and we could have not perfect, but we could have a normal here, and this would work out. It is exactly like it is currently, and it works. But assume we have a somewhat maybe scaled sphere, which is something like this. So if we would now transform the resulting normal vector as well, what would be our result? We would have one here, and then, yeah, we would have kind of one here and one here. And as you can already see, this is kind of wrong. It shouldn't be like this. So we need to apply a little bit more intelligent math to that. And essentially, we are not using the inverse matrix directly, but in order to convert between the world and the object space, which is this essentially, we have the world space, which is the transformed sphere, and we have the object space, which is always the unit sphere. We need to do a little bit more there. We not only need to use the inverse matrix, but the transposed inverse matrix. And you can actually go to Wikipedia and check the calculations behind that. If you really calculate this through and calculate this out, you will get this out of the equation system you are creating there, and you will know that you need to use the transposed matrix there. So let's start with that. So first of all, we need to convert our point, which is the world point, into the point which is in our object space. So let's call this object point. So now we are using the inverse of our transformation matrix. So self transform inverse, and multiplying this one with our point. So now we have our object point. After we have done this, we are calculating our resulting object normal, just as we have done before, using our now transformed object point and going from the center of our coordinate system, because we are now in our object coordinate system, which has the center of the sphere at 0, 0, 0, and always is a unit sphere of length 1. So we are calculating this one there and normalizing it. And now we need to do something. We need to transform back our object normal in object space back to world space. And this is where the transpose comes in. So now we have our world normal, which will then be the self-transform inverse, and we transpose this. And we multiply this with our object normal then, and now we have our normal in world space. But there is one caveat to think about here. If we would have a translation within this transformation matrix, we would have now changed the W component of our vector. So it is not a vector anymore with a W component of 0, because the translation would have changed this if we had using this transposing and then applying this, we would have essentially changed the W component. So we could have done this multiplication here, this transformation here with a 3x3 matrix, but we are essentially just hacking it a little here and saying that our world normal.w is always 0, 0. And so this should work out, and now we are just returning our world normal. Yeah, and now of course we need to make this mutable here, because otherwise we cannot change this later on. And I will add a comment here, hack, to ensure we have a clean vector, as due to the inverse transpose, the W component could be affected if the transformation matrix included a translation. So let's format this. And now we know why we are doing this actually. So yeah, do our tests still run? They should, because essentially for this default case we haven't changed anything. Perfect, our tests still run. So I guess let's then add the ones which are testing that the transformed sphere is working as well. So let me just copy them over quickly here. So yeah, there we go. More tests are always a good thing. So let me add them here, and let's see, there is already something broken here. So computing the normal on a translated sphere. So we have actually a sphere which is translated by a certain axis, and then we are using the calculation to get information from a certain point on this translated sphere, and we are expecting a specific normal here. So this is essentially just the basic values calculated here, which would be right. I've just taken them directly from the book, and we have the same thing here on a scaled matrix. Okay, and there it is missing an import of pi, because we need the value pi here then. And there it cannot, cannot by integer. Okay, yeah, I've seem to have made an error there writing the tests. It can happen always, because as I've said, I'm writing the tests without implementing this. It's the first time I'm implementing this when I'm recording this video together with you. So there might always be some errors in there. So yeah, it's essentially here the same thing. We are scaling the matrix now. We are using the Y and kind of squishing it together a little, and rotating it then around the z-axis, like we might have a sphere which is squished and then kind of rotated in a certain direction, and then we are calculating the corresponding point on the sphere here again. I've taken this as well from the book, and we are assuming a certain result there, which would be the normal then. So let's run the tests and hope that they are working. Okay, they are not. That's not good. So let's see what we might have done wrong here. We have one failure actually. We have the rotated sphere, which is not working out. Asserting fuzzy equality. The tuple 0, 1, 7 and something. Okay, so this would be this test here. And W00 is not fuzzy equal to 9, 7. Yeah, it is definitely not fuzzy equal. It's completely different. So yeah, let's just see what happened there. So the values kind of proportionally do not look that bad. So in proportion they are okay. So maybe did we normalize the output of our normal at... No, we are not returning the... is this maybe the problem? Let's normalize this vector here and see if this actually yields the correct result then. And yes, it does. We simply forgot to normalize the vector, which is, yeah. Maybe we should create a test for this just to ensure that the returned vector is normalized. So I guess we could do this. Let's maybe just copy this one here and make a test. The normal vector is always normalized. So we are getting this information here. We are getting the n vector here then, and then let's just assert that the normal vector is essentially the norm, so that if we normalize a vector which is already normalized, it shouldn't change anything. So this here should test that the returned vector is a normalized vector. So maybe we can, let's run this test here. Should work. Yeah, it works. So now let's remove this normalization here again, and then this test essentially should fail as well. So, okay, we are not getting a failure there. Yeah, because we are essentially not changing much there. The calculation would be the same because we are calculating in the normalized unit sphere space. So yeah, we would need to do the same thing with with a transformed one, I guess. So if we do the same test here with for example this one, which we know fails, let's do this one. Computing the normal, so let's call this the normal vector is normalized on transformed sphere. So let's essentially check this here as well. We have this one. We don't need this result, but we simply expect that n.normalize is the same as the returned vector. And we are checking this here then. So let's run this test as well. And now, oh, did I already put the fix in again? I did. So let's remove this one again. And let's, oh no, sorry, let's see. Yeah, and now two tests fail, and we can more or less directly see that the normal vector is not I've created a typo there. So it's not normalized. So let's put the normalized back in here again, and let's essentially fix this typo. Normalize, there is a Z missing, so this should work then. And now let's run the tests again, just to make sure everything is running. Okay, everything is running. So we have now the basics for the next calculations we need. So let's commit them. We can commit, we can now implement or calculate normals. No, I didn't want a diff, I wanted a status. So yeah, git add source body. Let's commit this. Edit normal add to intersectable interface. Git source sphere, git ci, implemented normal calculation at arbitrary points on the sphere. Nice. So we have implemented normal calculation. That's the first thing we essentially need, and we have done it for for normal spheres, for unit spheres, and we have implemented it for transformed spheres, which is very nice as well. So the next thing we need to talk about and to implement is reflection. So let's get back to our drawing board here, and yeah, this looks a little bit like a UFO. Okay, so let's see what we are talking about if we are talking about reflection. If we have, let's say, a wall here, and we have maybe a sun here or something like that, which emits light, and it emits a ray here, which goes into the wall and reflects out here. We should be able to calculate this. We should be able to calculate this vector here, the reflection vector, let's call it R. And there is essentially a quite easy way to do this, as we know that the incoming angle here, this one, should always be the same as this one. And this holds true in 3 dimensions as well. It is even easier to calculate this in 3-dimensional space now that we have the normals, because we can now have this normal here, which goes this way. It's the normal. And as you can see, if this is a 3-dimensional plane, something like this, and we now have something like this incoming vector here and this outgoing vector here, the normal, which is going up here, will be essential for us in calculating this reflection. So let's go ahead and calculate this around a certain normal. So what we essentially want is, we want to be able to calculate on any vector, given a specific normal, the reflection. So let's open up our tuple implementation. Let's get rid of the terminal here. And first of all, as always, let's add some of the tests. So let's copy in our first test here, which is reflecting a vector at 45 degrees. And it is essentially, if we have a vector at 1, -1, 0, and we have a normal vector of 0, 1, 0, we want the reflection vector, or the reflection of that, to be 1, 1, 0. And we can easily show this graphically and make us a little bit clearer what we actually have written down here. So we have our coordinate system here. And we have our incoming vector. It is it was -1, 1, I guess? No, it was 1, -1. So we have actually 1, -1. It is somewhere around here. So we have this vector here. And we have our normal vector, which is 0, 1, 0. So it is essentially this one here. It is our normal vector, is this one. And now the reflection of this one, this incoming yellow vector you see here, should then of course be like something like this. So it should essentially be 1, 1, 0. And as you can see, it is 1, 1, 0. It is going through this point, so it is a 1, 1, 0 reflection vector. And this is essentially what we are going to calculate now. Our test is already there, so we need this reflect method on vectors in order to reflect something around a given normal. So let's go ahead and implement this on our tuple struct. There we go. So we need fn, no, it should be a public function reflect self given a normal, which is another tuple. And it returns a tuple, of course, a reflected one, as it is. In order to calculate this, math is helping us as well. It is not that complicated, actually. You can Google it as well, how to reflect something based on a given normal vector of a surface. Essentially, what we are doing here, we are using the projection of a vector based onto this orthogonal space, and then calculating using the dot product, which is the cosine of the angle of the vector, which is the incoming one. And then we can actually work this one out, and we will get the following resulting term there, which will calculate our reflection vector. It is our incoming vector, which is of course our self there. So self minus the normal, So we are creating the vector from the normal to the self, and then multiplying this 2 times with ×2, and multiplying this with the dot product of of our incoming vector, which is our self in this case, and the normal. So dot product with normal. And this essentially will be then resulting in the new reflected vector. And as I've said, you can easily get this from Google or from any other resource. You can get this from Wikipedia or any math resource. And it's a little bit more complicated to get all this to work. If you are determining this formula. But it is working on the projection against the orthogonal space of the normal, and then back, and we get this reflection. And yeah, it is simply this formula, and it works out. So let's check our tests, I guess. Where is it? There it is. We have this at 45 degrees. So let's check this one. Cargo test. Is it running? And it is running. So it's time to get in some more tests. Maybe a little bit more complicated one, which would result or happen to calculate this for a slanted surface, which is somewhat other positioned in 3-dimensional space than the easy one we have here. So I guess we will take this one. Let's format this. And yeah, there's the same typo as before. And yeah, so you can now see that we have the square root of 2 over 2 here again as 2 of the normal coordinates there, because we are now somewhere rotated in space and going up there, and we want this vector to be reflected around this face. So let's test this again, and as you can see, this works out as well. Yeah, so we implemented reflection for tuples. So let's add this to our GitHub repository. Implemented reflection of vectors. Yeah, let's push this later on when we are finished with this chapter. Not now, so we can still change something if we want to go back. The next thing now that we have done the basic work of all of our things, we have now reflection and we have the normal calculation, is actually thinking about implementing the lighting. What the task we started out with when we were actually going ahead with this chapter to implement. And there are different lighting models out there because, of course, we could now do physics precise lighting simulation. We could simulate the path of photons against our world and stuff like that. And there are actually rendering techniques which do something like this. But we will use something called the Phong reflection model or the Phong Material model. And you may have heard of it by the term Phong Shading. It's around there. You may get it. If you are Googling something about 3D rendering, there will be the term Phong Shading somewhere. And essentially, Phong Shading goes back to to a guy named, I hope I'm pronouncing it right, I have no idea, Bui Tuong Phong. And he was the researcher who actually developed the Phong Shading. Phong Shading actually consists of 3 different types of lighting, which are then combined into one resulting lighting experience, which looks actually quite nice with regards to a kind of plasticky surfaces. It looks right for those kind of surfaces. There are other so shiny specular surfaces, polished surfaces, so to say. And there are other shading techniques for different other kinds of materials, but Phong is quite easy to implement and looks astonishing good, essentially. So let's take a look at these 3 components here. I've taken a picture here from the Wikipedia, which represents it quite well. So one component is the so-called ambient light, which is put into this calculation. And it is simply the light which comes from the fact that there is always some diffuse light around everything. It's the ambient variant of the light, which is somewhere in the scene, but you cannot essentially determine from which light source it came. Then there is diffuse light, which is coming from a specific light source. So there is some directed light source somewhere, and it is pushing out photons against your material or your object, and this is producing this diffuse light because it is somewhat maybe reflected from some other thing in the world and bouncing off everywhere, and so it's very diffuse. It's just lighting from the general direction of your light source, but it's not focused lighting. And then there is this focus specular lighting here, which you can see here, which is then directly light coming from the light source, directly reflected, sharp and focused from this specific light source. And if you combine all of them together, you can already see that this looks quite nice actually and quite realistic. And if you see this, the first one, the ambient one, would be something like the silhouette you have seen from our sphere because we rendered it in the last session. But this kind of something like this will be the result when we are finished implementing this Phong lighting model here. So the first thing we need actually to implement this one is a light source, because I've now just talked about a specific light source. So maybe we should just create our light source here, and let's call it light RS, and let's include it in our compilation then, pubmod light. So let's create our light in here, and for now it's simply a so-called point light. And a point light usually has something like a position in space, which should of course be public. It is a tuple. And then we need to import tuple, of course. Let's import the whole namespace here. And it has an intensity. So a point light is a non-directional light. It has a position in space. It is simply emitting light to everywhere from the position where it is. It is not directed like a spot in real life or something like this. It is more like the sun. The sun is there and it's giving out light, it's emitting light in every direction, and this is it doing from this position. And then it has an intensity, which actually is not only a value how hard it is, how bright it is, but it is a color as well. So the intensity is simply a color. We need to import this as well, of course. So let's do this, and oh no, there we don't want the whole namespace, we really want only the color there. And yeah, and we want to of course make this struct public. Let's format this code. And yeah, so we have now this basic point light struct, which is somewhere inside our three-dimensional world, and it has a certain color and intensity. So let's get the tests that the book wants us to create for this, which are essentially nothing spectacular. Let me paste them here. There we go. So it doesn't find the point light here because we need to now of course import this here. Then we can go ahead and delete this one, and of course now it doesn't know the new function because we haven't implemented this one yet. So essentially this test only goes ahead and checks that we have implemented a new function which sets the corresponding position and intensity arguments on our light. So let's quickly implement this on our point light here, which would be pubfn new. It takes a position, which is a tuple. It takes an intensity, which is a color. It returns a self, and this will be point light, position, intensity. And let's format this. And there we go. Let's run our tests, cargo test, and this should, oh, it doesn't. What have we done wrong here? Method not found, canvas color. Yeah, I guess I need to import those here. So let's import the whole fuzzy equality namespace here, and let's run this again. And now the tests are running. Okay, so nice. So now we have a simple point light which is positioned at one point in the scene, and we will use this later on for calculations, but for now we needed something to represent this. So now let's get back to our Phong shading model. And our Phong shading model actually needs something that is a material. In 3D rendering we have then a kind of a Phong material. It's a material which is represented by the Phong shading algorithm or Phong shading principle. And so let's create this one. Material RS. Let's add this to our module here, material. And even though the book tells us to implement this as the basic default material, I might want to later on implement other lighting models, other materials, because there are quite some mathematically nice and visually very appealing different materials out there. So I decided to do something like create maybe a material trait for now. We won't have anything in this yet. Let's make this public, and let's see how this works out later on. Maybe we will need to call it something else, because I guess we would need to implement the same enumeration technique. So maybe the term is lighted or shaded light. It's the lighted trait from being lighted, or maybe not lighted. I don't think this is the right word. Maybe it's illuminated. Yeah, I guess I like that. So let's create an illuminated trait, and this illuminated trait will maybe have some functions later on. We will see, but for now we then need an enum as well, which is a material. And we have seen this before with the body types, and I will essentially do the same thing here now for our materials. And we have a Phong material, which takes Phong material then, and this will all for now. And then we have a public struct called Phong, which is our Phong material. And our Phong material actually now will need certain different information. Our Phong material consists of, to create these 3 steps of lighting we've seen before, we have seen actually here, ambient, diffuse, specular, and then doing everything together. We need the following properties. We need a certain color. Yeah, our object, our material needs a color, so let's store this one. We have it as a color. Let's import this one. There we go. It's actually public as well, because we need to... Do we actually need to access this from the outside? I'm not sure. Let's not make this public yet. Maybe we will later on. We may need to read this. Yeah, let's make it public, because I want it public to be readable from the outside. That's quite nice. We need the ambient factor there. So this is simply a floating point then. Let's import our floating point type. This is essentially how much light is generally available there. How much light is in the scene that is not coming from any specific light source. So we have this ambient color value, we have this diffuse color value, which is a floating point as well, and essentially this describes how many diffuse lighting is kind of reflected by this material. It could be a darker one which absorbs more light, so it won't be this much. Then we have the specular, which is a floating point as well, and it's essentially how much specular, how much of the light will be used for the specular reflections here. And then we have the shininess. Did I write this right? Yeah, shininess. This is a floating point as well, and this will be used in the calculation with the specular effect as well, to make it how much light it kind of reflects out, how yeah, how reflective, how shiny, how polished it is in the end. So those are essentially the informations we need for our Phong model here. And now we will tell, I guess, the system that for one, we want that we haven't a function in there yet, but we will have one soon, that our material for now, implement illuminated for materials. So we want that our material implements this, and actually we want, damn, I removed the wrong one. We want Phong to, not Phong to implement this as well. So let's have this, and this. We have a public struct Phong, nice. So we need to implement this later on, but for now we want to implement within, or no, let's just first copy over our tests for our material, which are quite easy actually as well, because they will only ensure that we can do two different things. Let me copy them here, let me paste them here. That we can actually do two things, that we have a default Phong material, and we are using the default trait for that, which exists in Rust. We will see that in a second. And the default is actually, it has a white color, so a neutral color. It has an ambient value of 0.1. It has a diffuse value of 0.9, a specular value of 0.9, and a shininess of 200. And we want this to be the default material for more or less all our body objects later on. So we will couple this one with a sphere in a second, and have this as a default material for a sphere, because all our world objects, of course, need some sort of material. So the next thing we want, once we have implemented this one, we want to be able to construct this one with different parameters, of course. We want to, for example, change the color or change the ambient values or the shininess or actually anything. And then we want to make sure that our constructor transfers this nicely over to our object itself. So yeah, let's start by, I guess, implementing the default trait then here. Implement default for Phong, not phone, but Phong. And it already tells us we need to implement the default method then. So let's simply do this. Let's format this. And let's put the default in there, which would be, as I've said before, a Phong, which has a color of color new 1.0, 1.0, 1.0. It has an ambient of 0.1, it has a diffuse of 0.9, it has a specular of 0.9, and it has a shininess of 200. So let's format this. Why isn't my formatting is not working for some reason? Maybe because we still have oh no, because I missed a curly brace at the end, so now I should be able to format. I'm not able to format. That is what's wrong here? Expected identifier 9, expected oh. So yeah, now I can format this one, and now we have a nicely formatted default function here. So now let's implement Phong, and let's implement our new function, fn new. It actually is a public function, of course, and it takes a color, which is a color. It takes an ambient, which is of our floating point type. It takes a diffuse, which is of our floating point type. It takes a specular, it's floating point, and it takes a shininess, which is floating point as well, and it returns a self. And so it will return a Phong with color, ambient, diffuse, specular, and shininess. So let's format this. We obviously don't need this import here. We shouldn't need this as well. So the tests should now work. And we should make all of those public. So let's do this, I guess. We now have all of those public as well. So let's try and run our tests. And there are a lot of different errors, and we will see what's all of this about. Yeah, we have not imported our fuzzy equality here. So let's do that. I remember the first time when I had this problem, I was quite in despair to find out what was happening there. So yeah, now the tests are running, but there was a warning. What did we... Phong material can be constructed with properties. Did I actually not? Oh, I did not add the test annotation there. So of course the system does not know that this is a test and then tells us that it is never called. So let's do the tests again. Yeah, they are still running. So I guess now we could commit this, and I guess we should. So let's for now commit the, let's commit the light separately. Let's remove the material here again. Let's add source light, implemented basic point light structure. And then we want to add the material here again, add the lip again, and add source material, CI, implemented basic Phong. Okay, now let's not do this in one line because I want more text. Implemented basic Phong material structure. This commit furthermore contains the basic bootstrapping work to implement a generic material enum later on, which can be used in combination with the illuminated trait in order to implement other materials than Phong. So we did this. Nice. So what's next? Next is actually to give our sphere now a material. So now we have a material, so our sphere should have a material. So let me get the tests that are essentially being there for that it has essentially a new material, and let's copy this one over, I guess. Material, there we go. So a sphere has a default material, and the default material is the Phong material. So we need to, I guess, import this then. Is this even right? I guess this is not correct. Did I where's this now imported? Okay, it's imported here, but it's not used. Okay, let's check what I've done here. First of all, let's format this, because I've done something wrong there. So why is it here called Phong material? I guess we need to implement something else as well. I guess we need now to have within our material, I guess, our enum dispatching structure, we need the from implementation as we did with body before. So I guess first of all, let's import this one here, and let's not import this in the area of the tests. Where are we? Let's get there. There, we are not importing this there because we will need it later on here as well. So let's just import it for our implementation of the sphere as well. And now let's go over here and quickly import the from trait for our material. Yeah, I guess we should do this. So implement from Phong for material should be a quite easy implementation. Like, it should just be an implementation with from Phong, which is of type Phong, should return a self, and it should return a material material Phong, including the Phong one. So this should actually be enough now for us to create this one here, this material. Yes, nice. And yeah, of course, our sphere does not yet have a material field, so let's give our sphere a material field. So we have a pub struct here, so let's do it a pub material, which is a material. Material, yeah, there we go. And the trade bound material clone, yeah, we should be able to copy our, let's do this one, derive. We should be able to first of all copy and clone this one. We should be able to, I guess, debug print it for now. So yeah, we can't implement copy there, or we can't derive copy there because we don't have this one for the Phong. But as these are only some floating point values, we can easily allow copying for them as well. And now everything should be good, and this should work out. Binary operation cannot be applied to material. Yes, I see. So let's derive partial equality here as well, and then for Phong as well. And oh, we cannot do partial comparison for colors. Okay, we should simply derive this here as well. Shouldn't be a problem at all because a color only contains floating point values. So now, yeah, the initializer is missing the material, but we can fix this one, of course, by simply taking material. Maybe we should, wait a second, maybe we should implement default for this material thingy as well. That would be a good idea, I guess. So let's implement default for material as well. And default for material actually would give us material from Phong default. So let's just implement this there, so that if we want a default material, we can then, if we want to later change this at one position in our code, I like that, we can simply tell the material we want a default material and we will get one. This is nice. I actually like that. So if we have a transformation here, we of course need to do the same thing and apply a default material here as well. So now let's format this, and the test shouldn't be, the test one here shouldn't be red again. So no, it is not. So and we should actually change this. We don't want the Phong material default here. We want the material default here because we only want to ensure that a sphere has the given default material applied. And let's run those tests. And something is failing. What is failing? Fuzzy EQ defines, perhaps you need to implement it. Oh yeah, right. We haven't implemented fuzzy equality for our material. We should do that then, I guess. Yeah, so yeah, I guess we need to do this. So let's implement our fuzzy use create fuzzy equality, and we want all of this, and we want to implement there we go, fuzzy equality for no, that is not called like this. It is called like this, fuzzy equality with another material. Come on, material. Oh, for different material types, actually. I'm not sure. But let's try nonetheless. Implement fuzzy equality material for material, and so we are now implementing this function here, which is fuzzy equality. It gives us a self and an other t, which is material, should return a boolean, and so we need to kind of yeah, I guess we do a match here on the on other then, and if it is material Phong, essentially we will do the following. We will do something like we will do a match on, yeah, I guess we will do a match on self as well as other. Let me check if this works actually. So so if this is a material Phong and we are comparing it with a material Phong, then we want a ref to self and a ref to other here. Then we will, okay, self is not working, so let's call this one simply M maybe. Then we want to just dispatch it to M dot fuzzy equality with other. In any other case, we simply want to return false because, yeah, not found on for reference material Phong. Yeah, we haven't implemented this yet. We need to implement it then, of course. But we only want to compare those two if they are of the same material type. If they are not of the same material type, I guess, we simply can tell the system that they can't be identical. It is not possible because they are different materials, essentially. So now let's implement this one for Phong as well, and let's just check if it then works out as it should. So we are now implementing fuzzy EQ with Phong for Phong. And this one will be a Phong then, and the result will be a boolean. And so the result would be that we compare, that we return self.color fuzzy equality with other.color. And we are actually joining those together with self ambient should be fuzzy equal to other.ambient. And self.diffuse should be fuzzy equal to other diffuse. And we want self.specular should be fuzzy EQ with other.specular. And then we want self dot, what was missing, shininess should be fuzzy equal to other dot shininess. And now we are formatting this, and essentially this should, we can remove this then here. And now this should actually work. Okay, this does not yet work. Mismatch type, expected struct material Phong found, consider dereferencing. I see. So maybe, yeah, I guess I could dereference this here, but then I could actually get this directly here, and then it would be the right thing as well. So unreachable pattern node. Why is this unreachable? I don't understand that yet. Oh, because because this is always like, this is the only way it can be, maybe? Okay, so add a default case, different types to return false once more than one material exists. So let's create a comment there and then let's comment this out here. Because currently, as there only is one material, this is the only match that can happen here actually. So, okay, so now I'm fuzzy comparing materials, I guess. No, wait a second, it was here, wasn't it? Yeah, I'm now here fuzzy comparing materials, and I hope this should compile. Yeah, it does, and it works. So let's kind of add this. What did we change in Canvas? Oh yeah, we changed the thingy that color is has partial equality. So let's, I guess, commit all of this together. Implemented default material for spheres. This does include a fuzzy EQ implementation for materials as well. There we go. So we implemented this one. So now let's check that we can actually give it a different material, which would be nice as well, I guess. So let me put this test there. And for this, I want another kind of creation function. I'm not 100% sure what the best practice with Rust here is, but I will do it this way. Because I guess it will work and we will see. So let me just quickly fix up this one here. I want now material from, I guess, Phong with a new color. Do we need to import color then? Don't we use it there yet? Okay, we seem not to use it. And now, of course, we need to create this, and we want one with let's see, no transformation. So let's just create this function here, which then actually should do something like this. Pub with material takes a material, which is a material, and it takes a transform, which is an option transform. No, it's an option matrix 4, and it returns a self. And I guess we can we do something like, I would like to reuse the new, but the problem with the new is that it does not accept a transform, so it will then always put the default one in there. Maybe I will do it this way to find a better way to reuse the code here without changing all current invocations. I could easily add, of course, the material now to the new function, but this is exactly what I don't want. I don't want to touch all the different code paths I have now in the tests and everywhere else, which are already using this, just in order to add a property there. And I think I need to find out how to do this best in Rust. But for now, let's do it just this way by simply, I guess, doing something like getting a sphere here, like self new transform. And then we can say S material is our material, and then we simply return S. And oh, we need an FN here. The compiler even tells us to do. And there we have a mismatch of those, I guess, where... Wait a second, there should be a colon and there shouldn't be a bracket. Cannot assign to S material as S is not declared as mutable. Yes, didn't I do this? I thought about that I need to do this and then I didn't write it there. Okay, strange, but okay. So this should actually work out. So now our test should then actually run. Let's check cargo test. It compiles, it runs, perfect. So we have this as well. Get add source sphere ci allow material of spheres to be set. So let's push this. Why did I push this now? Just a reflex, I guess. I wanted to push this at the end of the session, but okay, I've now pushed it. No problem. So yeah, let's see what is then next. We now have our material. We have our Phong material with all these nice values. We have now a sphere which has a material, but now we of course need to kind of implement all of this color calculation and shading stuff. For each of our rays which hit our sphere surface. So we should implement a lighting function which we can call and ask more or less for the color that this hit of the sphere should have. So yeah, I guess, no, what have I done there? I've scrolled down. I guess we should do that. So let's do that. The first thing in order to do this is we want now to have a function in our illuminated trait. And we want a function there which we call lighting, I guess. The book calls it lighting. Yeah, it calls it lighting, yes. So we can ask a material about its lighting, and this function, of course, first gets the material and then it gets a bunch of different vectors to calculate the lighting for. First of all, it gets a light, essentially what we implemented before, which would be a point light. Let's for now put the point light in here directly. We might want to implement different kinds of lights later on, we will see. But for now, let's just use the point light here. We can easily refactor it in the future. So let's import this here. And the second one that it takes is the, what was it? The position, which is of course a tuple. Essentially the position on the surface we want to light. Then the I vector, which is the vector which is more or less coming from our point of view, from our eye, and looking at the surface. So we are getting an I vector here, which is a tuple, of course, as well. And we get the normal vector of the surface we are calculating the lighting for currently. So we need this, for example, in order to calculate reflections and stuff like that. And in the end, we simply want to return a color. So this is our lighting function. The lighting function should take all of those information about a specific intersection with an object, which is the light we have in the scene. It is the position of the intersection, the I vector, so where is our eye, where are we looking from at the scene, and the normal vector of the intersection point, and then calculating the lighting. Essentially using these values here, we can now in our Phong model calculate a proper lighting color, a proper shaded color for each intersection pixel with the sphere. So I guess we should do this. But first we need to delegate, as we have known here in our material, because now our material should cry out and tell us that it does not know how to do this lighting here. So let's do this, and let's delegate this down. Maybe I will use this enum, what was it? Enum dispatch create that I talked about in one of the last sessions, because it essentially does this for us what we are now doing manually. So we want this. Okay, I should have just copied this one. Let me copy this one here. Is easier. So let me copy this one, and then we are going to come on, we are doing a match against self, and we are checking if we are a material Phong or material M, then we can use the same code for every match in the future. And if we want a reference to this, and we want to do M lighting, and simply give or dispatch with all the information we have here, and return the result of this one. So this should work as well. But now our Phong lighting, yeah, it doesn't have this implementation as well. So let's copy it again and put it here. And then let's close it here. Let's close it. Let's format this whole file. And now let's quickly think about what we want to do with this lighting, and then we will talk about how to implement it. The what is quite clear. We want to shade according to the Phong lighting principle, using the ambient light, the diffuse light, the specular light, and the shininess. And essentially this is not that hard. I guess I will later on copy in the tests. Let's write this now, and then we will talk about these tests, because it is easier to explain the lighting during the implementation, I guess, of the shading model. The first thing we want to do is, and you can easily think about this, is we want to combine the color value that a sphere has with the actually color value that light has shining on it. So let's actually do this first. Effective light is simply the self dot, we called it color, I guess, and we are multiplying it with the intensity of the light. So this will give us the effective color value that our calculation should use later on, because now we have the color value of the point light combined with the color value of our material itself. It is important to know that we are only talking about the color here, not the amount of color or the amount of light that is taken into account later on. We will calculate this by determining where we are in relation to the point light and stuff like on later, but this is essentially now the color. And this is why that's why I did an error here. This should have been effective color and not effective light. So let's change this. And now we have it made clear that this is the color, because I was wondering there for a second myself. So now let's do something different, and let's determine where the light source, our point light source, is in relation to us. And we are simply doing that by taking our intersection position, which we are given, and shooting out a new ray, or better said, calculating the vector pointing in the direction of the light. And as always, how are we doing this? We are going ahead and taking the target point, which is the light's position, and we are subtracting the source point, which is our position. And in order to have a clean directional vector, we are simply normalizing this one. Normalize there, and let's call this light vector, I guess. Light V. There we go. So now the first thing we need for our calculation of our color, which should be the result, is we should calculate this one, the ambient light, first. And calculating the ambient light is quite simple. Therefore, we are only taking our ambient light should be, we are taking our now effective color, the combination of the light source color with the material color, and we are simply multiplying it with the effect it should have, which is self-ambient. So the amount of our ambient factor simply determines how much overall light should be put into this rendering there. So now in order to calculate the diffuse lighting here, we first need to determine something different. We need to know if the light source is on the same side as our eye and our surface, or if it is on the other side. So if we are looking from here onto this surface and our light source is on this side of the surface, it wouldn't actually be able to diffusely light this side up. So we can easily calculate this because we have our light vector now, which points to the light from our point of impact, and we have our normal, so we know how our face is oriented in three-dimensional space, and by simply calculating the dot product of the light vector with the normal vector, we essentially get the cosine of the angle between those two vectors, and therefore we can easily determine if it is a vector like this, where we have it on the same side, or if it's a vector which is, in this case, the cosine is a negative value, then it is an angle like this, and the light source is definitely on the other side of the surface. So let's calculate this one and call it light dot normal, because essentially this is exactly what it is. And let's do a light vector dot product normal vector. And now we can decide based on the light dot normal value here. So let's say if light dot normal is less than 0.0, then we are on the, or light is on the other side of the surface. So in this case, we have essentially two values here which we want to set, and let's maybe let's prepare our let mute ambient light, which we want to be a color, and we want let mutable, let's call it diffuse light, which is a color as well. And we want not only diffuse light, but specular light as well. So those are the three color components we need later on. And now let's, I guess, simply do something like set this here, which is already defined. And then we can do this here as well, because now we have a special case. If the light is on the other side of our surface, it cannot light it in a diffuse or a specular way. So we can simply say the diffuse light is color black, and we can say the specular light is color black as well, because there is no light. So what is happening here? Types expected, struct, canvas, color, found. Yeah, we are still not returning anything. That is fine. So else light is on the same side as the, or is on the side the surface is pointing to. And as you can see, the surface normal is really important with regards to lighting calculations. So there are different algorithms, for example, to create or refine polygon models, which we might implement later on, like, for example, Catmull-Clark and subdivide surface algorithms and stuff like this, which make them finer and nicer and stuff like this. And if you are doing an error there, you will have actually normals which are pointing into the wrong direction, and this could cause problems later on with your lighting calculations. But we will see, we will see. So now we are sure that we are pointing so that the light is on the right side of our surface. So now we can actually compute the diffuse lighting. And how would we compute this diffuse lighting here? It's essentially quite simple. We are using our effective color again, and we are multiplying it with the diffuse, the diffuse, where is it? Diffuse, the diffuse float value from our material to determine how much diffuse lighting in general we want. And then we need to multiply this one again with the light, and this is why we stored it before, dot normal. So why are we doing this? As I've said, this is the cosine of the angle between the normal of the surface and the lighting position. So if it essentially determines how much of the light should be reflected. So if the light is here and it is going directly here, the dot product will be, the vectors would be identical, the normal and the lighting vector, and therefore the dot product would be, in this case, 1, and we would simply put the full force of our light in it. But if we are at an angle like this, for example, and the light is hitting here, the value will get a lot smaller, and therefore a lot less of this light will be factored in, and so we get essentially this shading that we need here in the regions where we are getting away from the light. So essentially this is how we get this shading. Now, in order to calculate our specular lighting, our next step, our highly reflective parts of the surface, we need to not only take into account where the light is and where the surface normal is, so where the light and the surface is, but where the position is from where we are looking at the object as well. So first of all, in order to calculate this later on, it will make sense is we will actually calculate the reflect vector. Oh, I missed the let there. The reflect vector of our light vector. So we will see where the light should be reflected to from the surface, because essentially those are light, or this here specular, are direct light reflections into our eye. It's not diffuse light we are seeing, it's a direct reflection of the light source into our eye. So we need to calculate the reflection here, which we can quite easily do by taking the light vector and calculating its reflection to the normal vector. But we want the negative of the light vector, because we don't want the vector going from our position to the light, but the other way around. We want it from the light to our position. So now that we have this reflection, we can actually calculate the reflect dot, not fot, dot I, which is of course again the reflect vector dot product with the I vector, and essentially this is again then the cosine between our I vector, so where are we looking from, what are we looking at directly on the surface, and our reflection vector where the light is reflected to. So it's essentially more or less the same than the one we used here for our light dot normal one, the diffuse lighting, but now for the specular lighting. And again, we can know that if reflect.I now is less or equal to 0, then we know that actually nothing is reflecting to our eye because it is reflecting away from the eye. It's essentially the same thing as with the different side of the surface where the light was. Now, essentially the light is not, or the reflection is on the opposite side of our eye, so it can't be directly seen because it is reflecting into the other direction. So if this is the case, we can simply say that our specular light is black, because we simply don't have a specular reflection, because we don't see the light there. But if this is not the case, we first of all calculate our intensity of this reflection, and therefore we use our shininess material variable that we have. So let's take this one and calculate a factor here and get it. Essentially we are using this shininess and making the reflect factor, which we are then using to calculate like we did here with the light.normal. We are making this one bigger or smaller based on the shininess. So we are usually bumping it up a lot by simply calculating the reflect.I, and we are, is it then power f? We will see. We are just calculating it power to self shininess. So we are actually making it a lot bigger there. Is this actually? We will see. Let me get rid of all of this red here by simply returning a color black for now at the end, because I want to see the different problems there. Yeah. For example, that there is an unnecessary parenthesis around here, as I'm doing them always. And let's see. So yeah, we are not using all those values here now, but we have calculated our factor now. So let's get on here. And now we can actually calculate our specular light quite easily and more or less the same way as we did with the diffuse light. But now we need to only take the real light color and intensity into account, not the color of the material itself, because it is a direct reflection only, as you can see here, it is a direct reflection only from our light source, and so it is not changed by the material color itself, so by the color of our sphere. So we are only taking the light intensity, which is a color as well here. We are multiplying it with the with self specular, of course. So how many specular components should there be? And we are bumping this up by our factor. And essentially now we have calculated our specular light part as well. And now let me remove those lines here, and we can remove this color here again, because we now have every component calculated here in order to provide the real value. And what should this value be? Yeah, essentially it is part of this image. We want the ambient part, we have calculated it. We want the diffuse part, we have calculated it. We want the specular part, we have calculated this. And then we have our resulting lightning. And in order to essentially create this result, we just need to add all of them together. So yeah, let's simply do this. We have our ambient light plus our diffuse light plus our specular light, and this is our result. And if we put all of this together, we should essentially have now implemented Phong lighting, the Phong lighting model for our material, and so we can apply it to a sphere. And in order to make sure that we did, the book gives us a lot of different tests with regards to where our eye position is, where our surface normals are, and where our light is, and stuff like this. And as before, I have, of course, just written all of them down. So I will now essentially just copy all of them over, and I guess then we can run them and check if we implemented lighting correctly before we are going to actually use this to then render a sphere which looks a lot more three-dimensional than the one we saw in the last chapter. So let me copy over those tests here and just grab them and insert them here, I guess. So there we are. And now, so as you can see, we have something like we want to calculate lighting where the eye is between the light and the surface. Yeah, you can easily think about this. You have your surface here, you have your eye here, and you have your lighting here. And so your eye is between the light and the surface. Then we have something like lighting with the eye between the light and the surface, but the eye is offset by 55 degrees. So the eye is here again, the lighting is here again, our surface is here, but the eye then is maybe here because it is offset by 55 degrees. It's looking like this onto the surface. So and so on. There are a lot of those different test cases with something like the eye is on the opposite side of the surface or the light is on the opposite side of the surface and all of those kinds of stuff here. And yeah, but I guess we could just check if this runs now. And even though there were quite some warnings, the calculations seem to be perfectly fine. So let's check what I've done here. That actually isn't what he likes it to be. So variable does not need to be mutable. But why? When I'm setting it here, can I because I'm not changing it, I'm simply overriding it, I guess. So does this work? Okay, so because I'm not mutating the insides of this color struct, but simply just putting in a completely new color struct. And this seems to be okay for the compiler. Yeah, okay, that's fine by me. So let's clean up this a little bit, remove, there is some new line that shouldn't be there, this one should be there. Yeah, okay, nice. So I guess this worked out quite nicely, so I guess let's commit this. Git add source, material, commit, implemented, Phong Shading. So now we have implemented Phong Shading. So now I guess it is time to copy our last rendering here we did, which was chapter 5, and call it chapter 6 maybe, because we are now adapting this rendering here to simply apply the lighting of Phong Shading to our sphere and see how this looks. So first of all, I guess we should define a material, like material, which is then a material from, and it is a Phong material. Maybe we should allow a default Phong material by simply setting another color on it. I guess we could implement this, and I guess I want to implement this quickly. So let's just have another Phong creation thingy here. Where are we? No. Where is Phong? There is Phong implement. So let's just do a pub fn with color, and we are just taking the color here and returning a self, and I guess in this case we are doing Phong. We are returning a Phong with the given color followed up by self default, by all the default values. And I thought I had written, I had read that this would work and that we could do this. I guess I need to do it like this then. Yeah, so what is essentially happening here is now it's creating us a new Phong struct. It's using all the default values from this default thing we implemented here, but essentially is overriding whatever we have given it before. So it only takes from this what is not already defined here. So it's a short syntax for not taking everything out of this default now by property and putting it there. So now we should be able to easily create us a Phong material with a specific color, but without changing actually the different other properties. So maybe let's do something like a nice orange, like a 1.0, then we would need something like, I guess, in the area of 165 and 00 here. Let's try this one. And so now we should have a new Phong material with an orange color tone, and now we can do a new sphere with color essentially and give it the material and none. And I guess we need to compile it once for the system to acknowledge that there is a new binary actually, and now everything is everything is going wrong here. So let's see. Okay, maybe I need to restart the IDE quickly. Let me do that because sometimes it doesn't pick up on this as fast as I want it to. No, is it? Okay, now it's telling us what's wrong here. So there is something wrong with I have I guess some bracket or something like this. So we have a new color here that is closed. We have the font here that is closed. We have a material. Didn't we maybe not import this? Yeah, we did not import this. So let's import this. Let's import this one here. And no function or associated item named with color found for struct. No, it should be called with material, and then this should work. So now, and then we need a semicolon here, and now we have a sphere with a certain material here. That is a good thing, I guess. So I guess the next thing we need is we need a light source. So I guess let's add a light source, maybe just like we have a point light there, so let's edit point light new, and let's import this one. Why can't we? There we can import this one, and we need to give it a position, I guess. Maybe somewhere from above, like minus 10, minus 10 or something like that. So we could do this, and then we would give it a color. I guess for now we could simply give it a simple white light. Yeah, I guess this would work. Why is this not? Do I need to import this? What is it complaining about? This function takes 3 arguments, but 2 arguments were supplied. Okay, oh, there's a comma missing. There we go. So now let's format this, and we have our new light. So now we have a material and a light, and I guess now while we are calculating stuff here, and usually we just got ahead and wrote this yellow color, which by the way we can now remove. We don't need this anymore. We should be calculating the lighting, I guess. If we have no hit, we are still not calculating any lighting. But if we got a hit, we first of all need to get the position of our hit, which would be, I guess, maybe we should store this hit here. So let hit equals to get the hit out of this, and now if hit is something else than none, no, if can't we do something like if hit if let some hit yeah, I guess something like this. There was a syntax for this to do pattern matching in conjunction with, I guess I need to do it like this. Yeah, in conjunction with a if. So now our hit in here is some hit, and otherwise this pattern doesn't even match. So this is quite nice. So we can extract this one. So now we want the position actually of our hit, of the intersection, and inside the hit there should be isn't there a ray in there? No, wait a second, we know our array. So what we are doing here is we are calculating the position of our array, which we fired, which hit with the t value of the hit. So now, yeah, and now we get the position. That makes sense. So now we have that. We can actually calculate the normal, I guess, at this position. Yeah, so let's calculate our normal vector, which we have implemented before. So now we should be able to tell our, we actually have on the hit, we didn't call it object, we called it body. So from our hit body, we want the normal at the position, I guess. Yeah. So now once we have this, we need our I vector, so from where we are looking, and essentially this is just the inverse of our ray direction. Is it? Yeah, it is. So minus ray direction, I guess, I hope. So now we have everything there to essentially calculate our color. So let's get the color, let's get our hit body. We want to use the lighting function on our hit body, and we need to supply lighting not found on Ray Tracer Challenge body. Why not? Oh, body material. We need, of course, to do this on the material. And there we should be able... No field material on the Ray Tracer Challenge body. Oh, no, we need to extract the material then. Or we need to extract the body then. Is there an easy way to get to the material from a body enum we have there? Or do we need to now extract it? But this would be bad because we could only extract it using specific typing there. So yeah, so I guess we could do something like our intersectable now. But then the term okay, I guess we need to think about the term intersectable in the future. But for now, let's just maybe add a function called material here, which takes self and gives us material. Because I think every body should have a material, and therefore this should actually work. And we should define this in the trait, of course. So let's do this. Let's just put it there. And it then we should import material, and now we can implement this here using the same matching functionality and just get this from the material, from the sphere, and then of course the sphere needs to implement, yes, it needs to implement this this function here as well. There it is. So it needs to implement material, return a material, and simply return self.material here, I guess. So now we should be able to just get this one from calling material here. And then there is no method named lighting found for enum material. Yeah, but that's not true. Do I need to import something for this? Yeah, I need to, no, that was the wrong thingy. Where are we? We are here. I need to actually import, let's import material, illuminated, and Phong here. And then this should actually, yeah, now we have a lighting function here. So what is it that we should put there? I want the, thank you. This would be the light we defined above. Nice, we can do this, we can supply this. The position, we have now calculated this as well. Then we need the I vector and the normal vector, and we have all this. So let's supply this and we get a color out, and this is essentially the color we are writing back then we are writing back here then to the canvas, and now cannot move out of light. A captured variable in an fn closure move occurs because light has type. Okay, I guess we have, yes, we have not derived the cannot, I want to clone and copy this one, or to allow clone and copy, and of course I want to allow the debug printing as well, because it makes things always better for us. So now this error should have gone away, because now it can simply be copied in there. And let's check, what is this? Use of moved value array, value used here after move. So where essentially did we move that? Move occurs because array has type, which does not implement the copy trait. So chapter 649. So we are essentially here. It has not the copy trait. Wait a second, but we shouldn't need the. We shouldn't need this here. Why do we need to move? We don't need to move anything here. I just want the... For one, why shouldn't array implement copy? But I don't get why we need this there. But yeah, let's just make it work and worry about it later on. Derive, come on. Derive, copy, clone, and debug, because why not? Shouldn't be a problem. It's only a pair of tuples there. So now this is actually okay. So maybe let's reduce the canvas size for now to 512, because we have a lot more calculations now going on. But if we have done everything right, we should now be able to do, let me do a cargo build first and see. Okay, it compiled at least. So let's maybe do a cargo run, and let's select chapter, what is it? Chapter 6, and let's see what's happening. And it calculated quite fast actually. And now let's the moment of truth. Let's take a look at this output. Awesome. There is our shaded sphere. That is fantastic. We now have something that truly looks three-dimensional. I like it really much. Now, this looks like a three-dimensional sphere. That's great. So let's actually create a lot bigger version of this one. So I guess the optimization we did in the last bonus session by parallelizing all this calculation stuff now is paying dividends. It will take quite some time, but let's let me do something else. Let me first do something like, we want to build what was it? Was it production or something like that? No, prod. No. So let me just check, how can I build a non-development version of this, an optimized version, so to speak, so that we have the maximum performance out of it. So this would be build, package, no, lib, examples, test, bench, release. It was release. So let's do cargo build -- release. So it should now compile our whole it should now optimize our compiled result. So let's do this. And then we should actually have something like target here, release, and let's call chapter 06 here, and just see what happens and how long it takes. This is amazing. This is absolutely astonishing fast. Okay, so let's open this and let's see what this output is generated. It is now a 4096 by 4096 result, and it just looks gorgeous. I love it. This is awesome. This is absolutely awesome. Yeah, there we go. It's really fast. I wouldn't have thought that it is this fast. So, I guess let's just for fun, let's compare it with the development version. So this run chapter 6 now, it should be, yeah, it is a lot slower as you can see. But even though it is still quite fast actually. I think we got it down to under a minute in the end. By simply utilizing all of my processing cores which are available here, which are 8 cores. And yeah, this, of course, this is a lot slower because during the compiling a lot of optimization is not done there. I guess that the compiler will, for example, inline a lot of our code if we tell it to build a release version of it. But it's kind of astonishing how perverse the difference in speed is between the release version and this one. Essentially, this is exactly the same algorithm that we are just using there to calculate our sphere, and it is going on and going on and taking time and ticking away, and then writing our output. And it's just amazing how much faster the release build was. So even the writing of the picture is a lot slower. That is cool, making me a little bit nervous actually. So yeah, but it should be exactly the same output. Yeah, it is. It even opened it directly, so it is the same output. Yeah, that's awesome. I love it. I just love this one. So maybe we can now that we can quite fastly render this one, maybe we can I give this run thingy the release flag maybe? Is this working? Oh yeah, so oh, that's nice. So I can tell it to run the release version directly. Oh, that's nice. So maybe for now let's time them. I want to know how much time this takes. So how much time does it take in the release version? And okay, it takes essentially, wait a second, it took 6 seconds? Is this right? Yeah, okay, it took roughly 6 seconds. So how much time does the other version take? And I won't have you run through all of this again. So let's do jump through the time vortex again. Whoosh. There we are. It took 1 minute and 29 seconds. Okay, so it took 15 times as long. Okay, that is a lot faster, I would say. So yeah, maybe let's play around with these values. So yeah, we could, but yeah, maybe let's do one other rendering. Like we could, for example, change the color here. Like maybe we are creating some sort of, the favorite color of my fiance is actually violet. Can we do a violet here? Shouldn't this be? This should be. Should this be? No, this should be kind of. Maybe this should be a form of violet. Let's see. Let's render this. And yeah, it's nice. It's fast. I like it. So let's open this one, and now oh yeah, this one is nice. We could actually do something else. We could move our wall maybe closer, so that, no, if we would put it farther away, let's do maybe 8, the projection should get bigger. Let's check this one. Yeah, it takes a little bit longer now, as it needs to calculate the lighting for more pixels. if I've done this right. Yeah, and I think it got a little bit bigger. Maybe we can just move it back a little more, like maybe 11 or something like this. Let's try this. So let's check if this actually gives us something more, even bigger. Yeah, this is a nice big and round sphere. I love it. That is awesome. So yeah, let me put it make it a little bit smaller here so that you can see it. So yeah, this is actually the end result then of our finishing up chapter 6, which is the lighting chapter, and I really love this result, and if you have joined me on this course until this point, I hope you have as much fun with this result now as I am having, because now we have really ray traced our first visually appealing result, and I really much like that. And you can see that essentially the Phong lighting model is actually quite good with regards to materials which look like this. There are different other lighting techniques. As I said, we might implement them later on. I'm not sure. I guess the book doesn't have information about those, but maybe once we are finished with the book, we will go ahead and implement other stuff on this ray tracer, because currently I have a lot of fun. So maybe this will go on. So yeah, I like this very much, and thank you for joining me again. And in the next session, we will essentially do chapter 7 then, or start with chapter 7, which will allow us to create scenes. And this would imply that we have more than one object in the world, and that we can then render and ray trace stuff within this scene. I'm not 100% sure if we are already doing something like a camera then in this scene, but I guess we will, so that we can then implement something that we can kind of move around and look at the scene from different directions and stuff like that. And yeah, I'm already looking forward to this as well. And until then, have fun. You can find all the resources and the code in the description below. I will commit it just after this session and push it there. Yeah, if you liked this video, please subscribe to my channel to be informed of new videos which will come up in the future. Hit the like button, the thumbs up button, and maybe post a comment under one of the videos or under all of them, and tell me what you find very interesting. And yeah, I hope you enjoyed this, and I will see you next time. Bye!